we're very happy to have here today Miren Raj Radia from University of Cambridge. He's doing his PhD under the supervision of Professor Ulrich Sperhak. So, Miren, the stage is yours. Thank you.
Thank you very much, and thank you for the invitation as well, and thank you everyone for attending. So this presentation, as you can see, has got a long title that I just kind of ripped from the paper that we published. This work was done at the end of last year and kind of finished at the beginning of this year, in collaboration with my supervisor, Dr. Sperhaker, Emanuele Berti, a collaborator at Johns Hopkins University in the US, and another PhD student, Robin Croft. We put this on the archive in January and it was published in May. But I guess the short title for this talk is Kicks from Eccentric Black Hole Binaries. Anyway, let's move on. Briefly, I'll just go through the introduction and motivate why, what's the point of what we're doing. And then I'll talk about the setup and methods that we use. So kind of go through a brief recap of numerical relativity. We'll talk about the black hole binary configurations that we considered, the particular numerical implementation, and the diagnostic quantities that we looked at in order to compute the results, which is the kind of final part of the talk. So yeah, the introduction. So first of all, what are kicks? So it's been known for a long time that gravitational waves carry energy and angular momentum, but the carrying of linear momentum from gravitational wave by gravitational waves is been known for slightly less time. So an asymmetric emission of gravitational waves can carry a net linear momentum, and because of conservation of momentum, basic physics you learn at school, we know that if there's a net linear momentum in one direction, by conservation of momentum, we have to have a recoil, or as we call it, a kick. This is imparted to the emitting system, which in our case would be black hole binaries. So in the case of black hole binaries, the necessary asymmetry can be generated, for example, by unequal masses or misaligned spins. And in this particular work, we considered unequal masses. But the asymmetry is important. We can't use an unequal mass non-spinning black hole binary will not emit a net linear momentum by symmetry, so there will be no kick unless there's something wrong with your code. So yeah, why do we care about kicks? Well, one reason we care about kicks is the astrophysical consequences. So it's pertinent to compare the kick velocity that we get from numerical simulations with the escape velocity of various astrophysical environments. So I've given you some examples here that come from astrophysics. So for globular clusters, the escape velocity is on the order of tens of kilometers per second. And we know that even before this work, that quasi-circular non-spinning binary black hole mergers, so where the kicks are generated by the asymmetry comes from unequal masses, we can generate kicks on the order of hundreds of kilometers per second. So these will escape globular clusters as an example. We can also use kicks to estimate the rate of second generation mergers between black holes that have already formed from first generation mergers. And we can use kicks to constrain growth theories of supermassive black holes at the center of dark matter halos. Yeah, so furthermore, the study of recoiling gravitational wave emitters may help us further understand astrophysical sources. A recoiling post-merger black hole can induce a blue or a red shift on part of its gravitational wave signal, and this may be exploited in future gravitational wave observations with next generation detectors to directly measure kicks. And then we should take these kicks into account, and these effects should be taken into account with future ring down tests of general relativity with third generation detectors in order to avoid systematic biases. Okay, so I've talked about kicks. Now let's move on to eccentricity. So why do we consider eccentricity? So I guess the main reason is we still don't know how black hole binaries form, and there are several suggested formation channels. Currently, it's widely believed that most black hole binaries form from primordial star binaries in isolated systems, but there are some recent studies which suggest that the proportion of black hole binaries that have formed dynamically are much higher than what were previously thought. So in the isolated binary system, gravitational wave emissions acts to circularize the orbit. And And this is why until recently there hasn't been much of an interest in eccentricity, and most template banks for gravitational wave detectors have tried to, they've tried to make their black hole binaries as quasi-circular as possible. But since these studies have come about, orbital eccentricity is expected to be a distinguishing feature of dynamical formation channels in for example, globular clusters, galactic nuclei, and we can use eccentricity as a means of determining the formation channels of black hole binaries. So there has been some work on the first and second LIGO observation runs, and there was no evidence from this paper that there was any eccentricity in these two observing rungs. But obviously, in the third observing rung, there's been far more events, so much more things to look at. And in particular, GW 1905-21, which was the very, very high mass merger, very, very short burst. There are studies that claim that this is potentially consistent with eccentricities as high as 0.7, but the signal was so short that I guess it's a bit hard to say, and people have said this has been lots of other things as well. Another reason to consider eccentricity purely for academic reasons is just another way to accentuate the asymmetry, just to see how this asymmetry plays into the kick phenomena and see what effect it has. Since kicks are caused by asymmetry, it's a natural ingredient to consider to enhance or modify the kick. Okay, so that was the motivation why we did what we did. So now let's move on to just some basic setup. So this is kind of going through a brief recap of numerical relativity. I'll probably go through this quite quickly, as I assume at least most people or some people have seen this before, possibly many times. So we use the 3+1 formalism to evolve, and in the 3+1 formalism, we foliate our space-time by a collection of spatial hypersurfaces, sigma t, indexed by a global time function t. We then choose these adapted coordinates where the metric takes this form, where the alpha is the lapse, beta I is the shift, and gamma ij is the spatial metric on each hypersurface. The lapse and shift are our gauge variables, and these determine how our coordinates behave as we evolve from one hypersurface to the next. So furthermore, we introduce the extrinsic curvature, which describes the curvature of the slices within the embedding of space-time. But furthermore, you can roughly interpret it, from this definition as the time derivative of the metric. This is the lee derivative in the normal direction. I note that the sign convention of the extrinsic curvature is standard in numerical relativity, but differs to that of other conventions. So if we project the Einstein equations in the normal and spatial directions, we get the ADM evolution equation and the constraint equations of general relativity. But unfortunately, the ADM evolution equations are only weakly hyperbolic, so they're not suitable for numerical evolution. So we need to think of another method in order to evolve general relativity. So how do we do that? So one of the most common ways, which is what we do, is we switch to a kind of a reformulation of the Einstein equation. So we introduce a conformal decomposition of the metric and decompose the extrinsic curvature like this. So notice that this chi conformal factor factors out the metric determinant, and this allows and chi will smoothly go to 0 when the physical spatial metric gamma ij, when these metric components blow up, for example, in a black hole and near the center of a black hole, and the conformal metric, that's gamma tilde, this remains well behaved because chi removes the blowing up of the physical metric. Furthermore, we introduce the conformal connection functions, or the gammas, really, the gamma tilde, which is just a contraction of the Christoffel symbols with respect to the conformal metric. And this is the basis of these are the kind of basic key steps that we use in the strongly hyperbolic formulations in numerical relativity that are very common today in finite difference numerical relativity codes. So the two formulations that we use are the BSSN OK, or sometimes just shortened to BSSN formulation, and the CCZ4 formulation. So in the BSSN formulation, the evolution equations that you get are further modified using the constraint equations that arise in order to make the system more strongly hyperbolic. But in the in contrast, conversely, in the CCZ4 formulation, an extra 4 vector, the Z vector, is introduced, which vanishes on the constraint hypersurface, so on physical solutions in solution space, and there's no further modification. You just add this extra 4 vector to the Einstein equation, and it vanishes on physical solutions. Furthermore, we also need to, so I said that the lapse and the shift are our gauge variables. We need to choose gauge conditions that will allow us to stably evolve moving black holes. And the standard way to do this with the BSSN and CCZ4 formulations is the moving puncture gauge, which came about in the mid-2000s. And this has proved remarkably robust at evolving black holes over the past 15 years or so. But unfortunately, it's still not understood rigorously why the moving puncture gauge works so well, whereas other gauges, which also are part of a strongly hyperbolic system, these fail for moving black holes, but the moving puncture gauge works so well. There are lots of heuristic arguments, and there have been many papers published on this, but if anyone proves this, please let me know. Okay, so we're interested in gravitational waves, well, the kicks that we get from gravitational waves. So we need a way of extracting gravitational waves in our numerical simulations. There's quite a few different ways to do this, but probably the most common way to do this is to use the Newman-Penrose formalism, which I'm going to describe here. So the Newman-Penrose formalism starts by introducing these 5 Weyl scalars, but the one we care about is psi4, which is just a contraction of the Weyl tensor with some null tetrad vectors, some null vectors that come from this complex null tetrad. So this complex null tetrad is the whole basis of the Newman-Penrose formalism. And in the Newman-Penrose formalism, the space-time metric is written like this. But finding this null tetrad numerically is non-trivial, and we kind of take the flat space the null vectors, and then we apply Graham-Schmidt orthonormalization procedure in order to construct an orthonormal tetrad, and then construct a null tetrad from that in order to construct the suitable null vectors to make our psi4. So you're probably familiar from undergraduate or gravitational general relativity courses about what are gravitational waves. They arise and they're plane wave solutions to the linearized Einstein equations. And you probably will remember that you can, in transverse traceless gauge, you can write there are 2 independent components. There's the H plus, which is the plus polarization, and then there's H cross, the cross polarization. So you can show in the linearized approximation for a plane wave in this transverse traceless gauge that psi4 is just roughly 2 time derivatives of the H plus the strain in the cross polarization, with the imaginary part being the cross polarization, like that. So what we do is we typically extract the values of psi4 on multiple spheres at fixed finite coordinate radius. We can then extrapolate these to null infinity by assuming the asymptotic fall-off of psi4, and this asymptotic fall-off is known as the Peeling property. Okay, so now I'll talk about the black hole binary configurations that we considered. So I've drawn a kind of schematic diagram here. So we considered 4 different sequences. So the names SQ23, SQ12, LQ12, and SQ13. So the S and the L correspond to short and long, and then the ratio is the mass ratio that we considered. So there'll be 3 different mass ratios: 2 to 3, 1 to 2, and 1 to 3. And the reason we chose these mass ratio was to cover the interesting part of the plot. So if we plot the quasi-circular kick velocity against mass ratio, I will show this plot later on, then we chose the interesting range. So there's a local maximum in this plot, and we chose these mass ratios that cover this local maximum. So first of all, what is a sequence? So a sequence is constructed by first finding the tangential momentum. So for one configuration that gives a quasi-circular configuration. So we fix D, the initial separation for one configuration. Then we solved using a post-Newtonian formula for the tangential momentum. So you can see P points in the tangential direction, given the specified initial coordinate separation and the mass ratio. And then we progressively reduce the tangential momentum whilst holding the binding energy, which the formula is at the top. So that's just the difference between the ADM mass and the two total black hole masses. We hold this constant. And this means the initial separation D increases. So if I show just a video, short animation of that, you can see that as we reduce P, D increases as the binding energy is held constant. This was a somewhat of an arbitrary choice to keep the binding energy constant, rather than, for example, the initial separation. But the reason we chose to do this is this allows the in-spiral phase of our simulations within a sequence. So for P very small and P, the largest P value that we considered, this allows the in-spiral phase of the simulations to be comparable in that, you know, if we just hold D constant and reduce P, then the case where P equals 0, the head-on limit where the eccentricity is infinite, I guess, the in-spiral, or well, the collision would be very quick. So we wanted it to be more comparable. So you might ask, so why do we consider two sequences for Q equals a half? And the reason is because we considered a longer one because we first conducted the shorter sequences, and then we noticed some artifacts which I'll talk about later, and we wanted to extend this. We wanted to see if this was due to the short in-spiral phase, but actually we found that the longer in-spiral phase accentuated these artifacts, which I'll talk about. So I keep talking about eccentricity, but actually there isn't a well-defined notion of eccentricity in full general relativity, and we use an estimate coming from post-Newtonian theory. There's various different ways of calculating some approximation of eccentricity that reduces to you know, the usual Keplerian eccentricity in the Newtonian limit. But we chose one coming from post-Newtonian theory, and I put the archive link at the bottom. And in this particular formalism, there are three eccentricity parameters, ET, ER, and E phi, and they're related to one another. The choice of which one to use is somewhat arbitrary. They give relatively similar results. And in the Newtonian limit, they reduce to the usual, you know, they all reduce to the usual Keplerian eccentricity parameter. But this eccentricity estimate should really be taken with a pinch of salt. As I said, the in-spiral phase of these simulations, even the long sequences, is relatively short. So the short sequences do about 3 orbits in the quasi-circular limit, so that's the largest p values, and the long sequences do about 6 orbits. Nevertheless, this estimate provides us with a means to quantify the deviations from quasi-circularity. Okay, so let's briefly talk about the numerical implementation. So I used the GR Trumbo code to evolve the 2 of these short sequences for SQ23 and SQ13 with the CC4 formulation. And my supervisor, Uli Sperhacker, he used his own lean code, which has has been used for over a decade to evolve black hole binaries. And he uses the BSSM formulation, and he did the 1:2 mass ratio sequences. So I think this is the first time that GR Trumbo has been used in a study involving conventional binary black holes. GR Trumbo was developed and written mainly for more exotic space-times rather than just conventional binary black holes, but it was a useful test for this project to show that we're capable of doing so. So both codes use the method of finite differences. So that's probably, when you're an undergraduate, it's the canonical way of solving partial differential equations, but by far not the only way of solving partial differential equations in the computer. And in finite differences, the continuum is approximated by a discrete number of points. And in order to kind of, we use the method of lines for evolution. And in the method of lines, the spatial discretization is separated from the time stepping, the time discretization. And this allows us to use standard ordinary differential equation integration methods for the time integration. So in particular, we just used the Runge-Kutta for RK4, which you may recall from your undergraduate studies or graduate studies. So both codes use Berger-Oliger style mesh refinement. So mesh refinement is used to reduce computational expense. It would be prohibitively expensive to use the same resolution everywhere in the computational domain. So in mesh refinement, the grid consists of a hierarchy of meshes with increasing resolution around the black holes in order to suitably resolve them. So Lean uses the trusted and tested method of moving boxes, which has been used for over a decade, 15 years or so, or much longer, to evolve binary black holes, and is pretty robust. And GR-Trombo uses a slightly more adaptive mesh refinement, which is why I say it was developed for more exotic spacetimes. But this caused us, a few issues in. It took a bit of work to get GR-Trombo's mesh refinement to play nicely with binary black holes. So this was part of the project. It was showing that GR-Trombo is capable of evolving binary black holes with suitable accuracy. And both codes use the two puncture spectral solver, which is kind of the de facto standard code for moving punctures, for puncture initial data, for Bowen-York puncture initial data. So that's spinning black holes that also have a boost as well. So Bowen-York data is a conformally fat solution of the constraints for multiple boosted spinning black holes. In the case of one black hole, it's not exactly the Kerr solution because there don't exist conformally flat coordinates for Kerr, but it does include some extra stuff which we call the junk radiation. And this when we start evolutions, this junk radiation just propagates outwards to the outer boundaries of our computational domain. Okay, so I've talked about the numerical implementation, and I've talked about gravitational wave extraction. So how do we calculate the radiative momentum in gravitational waves? And we use this formula here. So we actually calculate, in addition to the radiative momentum, we actually calculated the radiated energy and the radiated angular momentum. And in order to do this, we extracted the values of psi4 on spheres of finite coordinate radius, and then we calculate these at finite radius, but you'll notice in this formula I have a limit as r goes to infinity, and then what we did is we extrapolated the results. So we calculated at multiple finite extraction radii, and then we extrapolated the results to infinity and used this as an error estimate. We extrapolated the results to null infinity to obtain an error estimate. You'll notice that I have a T0 integration limit there. And we choose that T0 to exclude the contribution from the junk radiation because we don't want that to contribute to our physical values of radiated momentum and energy and angular momentum. And then in order to obtain the kick, because these kicks are very slow, we just divide the radiated momentum by the final mass. And the final mass of the black hole is computed using the difference between the initial mass that the two punctures code tells us is the initial total ADM mass of the spacetime, and the radiated energy that we calculate using a similar formula to equation 5 here, but for the radiated energy. The final spin is computed similarly. In addition to computing the radiated momentum using equation 5, we also use this much more complicated looking formula to compute the radiated momentum using the multipolar amplitudes. So you can expand psi4 as in terms of the spin weight -2 spherical harmonics, and we call these and we've given the symbol for these amplitudes the psi, these lowercase psi LMs. The details of this formula are kind of unimportant, but what should be noted is that the contribution to each L tilde and M tilde in the sum involves an overlap between different modes of psi4. So you can see here we've got this L -1, M +1 here, and we've got it's multiplied by this L tilde and M tilde here. So the lots of different values of mixing, of mode mixing between psi LM and other values of the multipolar amplitudes. Okay, so now let's move on to the results. Oh, before we do that, I've got a short visualization. Let me just play. So this is a visualization I generated, I think, from one of the 3-to-1 mass ratio configurations. Unfortunately, because the kick is only hundreds, about 180 kilometers per second in simulation time, it's very slow. So you do have to look very, very closely. I recommend, looking very closely at your screen right at the end after the black holes merge, and you'll see they just start to move. And I've also kind of the red and the blue that you can see the orange and the blue, which you can see very faintly. These are the gravitational wave emissions from the binary black hole system. So you'll see when they merge, there's a burst of radiation. So that's the junk radiation, I think, that's coming out. These are just random fluctuations now. So they in spiral, then they merge. You can see the burst of radiation. There you go. And then you have to watch very, very closely, but you'll see that it's just moving upwards in a few seconds. I have sped it up quite a lot, actually, because this effect is so small. But you can see it's moving up now. So I'll just play that again in case you missed the moving up of it. But yeah, it's a very small effect in simulation time, because we use units where c equals 1. So in terms of the speed of light, which is obviously order 10 to the 8 kilometers per second, and these are 10 to the 2 kilometers per second. It's not easy to see. But in any case, it's nice to see that you can see it if you play around with the visualizations. Okay, so that was a short visualization. The main results, I guess, our main kind of plots for this project are 4 figures like this. I've got 2 on this slide and 2 on the next slide. One for each sequence of black hole binaries that we considered. So there's a lot going on in this plot. So let me just explain what's going on. So like I said, these are our main plots for the SQ23 and SQ13. You can see with the kind of the labels here, the gray labels here. So in the top panel, we've plotted the kick velocity in kilometers per second as a function of the initial tangential momentum on the horizontal axis. So the kick is just the blue solid line. In addition, on the top panel, we've plotted the contribution from different partial sums in the complicated overlap formula for the radiator momentum. That was equation 6. So if I just go back, you can see that there's a sum here for L tilde and M tilde. So I've the yellow dash, the green dash, and the purple dot dash, well, the purple green dot dash. These are only including the L tilde less than or equal to 2, only including the L tilde less than or equal to 3, and only including the L tilde less than or equal to 4. The red dash contribution is the contribution only from the L equals 2 multipolar amplitudes of psi 4 to the radiation momentum. We thought maybe we'll just see if these partial sums, if these oscillations that you can see, if they were a result of including higher order multipoles. But you can see that they are well, they're still there, but they're less accentuated. So that's the top panel. Also, you'll note that I've provided the post-Newtonian estimate for the eccentricity in this kind of non-linear axis on the top. But this is just kind of to give you a rough idea of what's going on. In the bottom panel, I've plotted the radiated energy and final spin of the post-merger black hole that we measured. You can see that there are oscillations in this too, but they are less pronounced than in the oscillations for the radiated momentum. And each individual cross in the bottom panel corresponds to a separate simulation. So there were lots of simulations that we conducted as part of this study. Okay, so this is the kind of you probably barely noticed the difference, but these are the results for the 2 other sequences. So the 2 sequences for the mass ratio 1 to 2. So the short sequence and the long sequence. So let's just go through the results. Let me just explain what's going on. So our first result is that the kick is maximized for moderate eccentricities. So you can see here about eccentricity about 0.5. And that's true in all cases. So if I go back to the previous slide as well, it's roughly 0.5 or close to 0.5, moderate values. For SQ23, SQ12, and LQ12, so for the more equal masses, the less unequal masses, the amplification in the kick compared to the quasi-circular value, which is the rightmost value, the largest momentum value, because remember we started with the quasi-circular kick with the largest momentum and reduced the momentum, so the eccentricity increases as you go leftwards. You'll notice that the maximum value here that I'm showing with my laser pointer is about 25% bigger than the quasi-circular value. But for the 1 to 3 mass ratio sequence here, it's only about 12%. We also get a slightly smaller kick compared to the quasi-circular value for lower eccentricities. We get these local minimums here where the kick is slightly slightly reduced compared to the quasi-circular value for random eccentricity values. So I guess in addition to this amplification and decrease in the kick, we also get this oscillatory pattern, which I've already pointed out in the kick as a function of the tangential momentum p or the eccentricity. And these oscillations, as I've pointed out, seem to differ in their location to that of the radiated energy and final spin. And the reason we added the long sequence, as I said, was to add it to check whether these oscillations were due to the short in spiral phase of the shorter sequences. But remarkably, you can see in the longer sequence that there are even more oscillations and they look even more pronounced here. The next result, I guess, is that considering the various truncations of the sum for the radiated momentum, we see that the oscillations are present at every level. Even if we only include the quadruple contributions only, that's the red dashed line. But the effect is somewhat milder. The oscillations are less pronounced. And we see that increasing the number of terms in the partial sum, so increasing the number of higher order multiples, this seems to systematically decrease the kick. So those are kind of our results. I'll just kind of summarize them here. So yeah, the maximum kick occurs at eccentricity 0.5, and it's about 22%, 25% larger for the more equal mass ratios, and about 12% larger for the most unequal mass ratios. We get this oscillatory behavior. In V is a function of P, where P is our tangential momentum of the initial binary black hole. And if this pattern continues, we would expect the kick to depend highly sensitively for even longer in spirals. But I preface this statement with if, because extrapolating based on 2 data points, we only have one short sequence and one long sequence that are comparable, is not usually the most reliable method. But this is an interesting result nevertheless. Yeah, so fewer, less pronounced oscillations in the radiated energy and final spin with different locations of extrema, and the oscillations are present in all considered partial sums of equation 6, but somewhat less pronounced. And these higher order terms with L tilde greater than 2 seem to decrease the kick. Okay, so I mentioned the graph of the quasi-circular kick against mass ratio. So it's usually plotted against a symmetric mass ratio. So what we did is I overplotted the kind of oscillations in the kick on this plot. So this figure shows the range of recoil velocity is obtained for each sequence. The blue line is a functional fit coming from this paper here of the kick velocity against the symmetric mass ratio eta in the quasi-circular case. So there's only one value for each mass ratio. So the short sequences are in gold, in this gold color, and the long sequences in red. We've excluded the plunge limit, so those configurations with the tangential momentum p less than the value that gives the maximum. So basically, if I go back to this figure here, I've excluded everything to the left of my laser pointer here. So everything here is excluded. So I've only included the oscillations in the kind of interesting part of the plot. Otherwise, the bottom part of the range would just go to 0 because the kick is very, well, it would go very, very small in the limit, in the head-on limit. And we were interested in the oscillating regime. And note that, as I said, we've covered the regime. We covered an interval containing the maximum kick. So the maximum kick is about here in the quasi-circular case. Okay, so we now try to understand the origin of these oscillations in the kick against the tangential momentum. We were inspired by the knowledge coming from the superkicks. Now, superkicks are caused when you generate kicks not from unequal masses, but from spins that are misaligned, but both lie in the plane. So you start your black holes in the plane, but with equal and opposite. So the spin lies in the orbital plane, but in an equal and opposite direction for each black hole. So this configuration is known as the superkick configuration, and this generates very large kicks on the order of thousands of kilometers per second. And obviously, with superkicks, there's the freedom to choose the direction of the spin. And we know that in the superkick case, the orientation of the spin is picked out, and there's a known sinusoidal dependence of the kick magnitude on the angle of the spin in the orbital plane. So in our case, we don't have a spin direction. Our black holes are non-spinning. So the only real special direction, given that we consider eccentric binaries, is the apoapsis. And just as a reminder, the apoapsis is the axis along which the separation of the two objects is greatest in the Kepler problem. So you may be more familiar with the term aphelion, and this is the term specifically related to the sun. So the apoapsis is the more general term. So we wanted to look at the Infor direction of the black holes relative to the apoapsis or the periapsis, the smallest, the axis of smaller separation. But unfortunately, there isn't really a good definition of Infor direction. It's very hard to quantify. So instead, we looked at the angle of the kick in the orbital plane. So the kick lies in the orbital plane by symmetry, and we can argue that if we interpret the gravitational recoil to be predominantly generated by the excess beaming of the gravitational waves in the direction of the smaller black hole here, remember that they have the same momentum, but this smaller black hole has a smaller mass, so it's moving faster. So it kind of beams the gravitational waves more, focuses it more in the direction it's going. And if we interpret it as being as this causing this being the cause of the direction of the recoil, this angle can serve as an approximation to the Infor direction. And I've reproduced this figure from this paper. So what we did is we plotted the kick against the kick angle theta, which is just the angle in the orbital plane. So this, and I've added 2n pi. So I've added suitable multiples of 2 pi to make this curly theta a monotonic function of the initial tangential momentum p. So I've just added 2 pi appropriately to do that. And here you can see that the oscillations have an almost constant frequency, which doesn't seem to depend on the mass ratio. It seems to be almost independent of the mass ratio. And naively, we might expect 2 pi periodicity. We might just expect 2 pi periodicity, but we mustn't forget apsidal precession. For example, recall the solar system tests of general relativity. So the apsidal precession of Mercury, and this effect of GR would expect to slightly decrease the period of 2 pi. And actually, this is in fact exactly what we see, that the period of these oscillations, the wavelength of these oscillations is just a bit less than 2 pi. And we believe this is the cause of our deviation from 2 pi periodicity. Okay, so we then wanted to understand where this was coming from. So what we did, we just looked at, as I've already pointed out, the radiated momentum can be calculated from contributions of an overlap contribution between different modes, multiple amplitudes of psi4, these lowercase psi LMs. So if we go back to equation 6, which was that complicated formula I showed you earlier, the L tilde equals 2, M tilde equals -2 term involves contributions from the 2, -2, 2, 1, and 3, 3 multiples of psi4. So yeah, I've already said about this equation 6, the complex interactions. So on the left, we plotted the 2, 2 and the 3, 3 modes of psi4. And what we've plotted it for are for 2 configurations, 2 consecutive local extrema on the plots of v as a function of p. So if I go back all the way to here, if I pick, say, this local minimum here, and then the next local maximum, say here, that's what I mean by 2 consecutive extrema on that plot. So what we noticed, this is just purely observational, is that the modes appear to be more in phase for the bigger kick. So the bottom value is the bigger kick. So this is the extrema, the maximum, local maximum in that graph. You can see it seems to be more in phase here at the peak amplitude, whereas for the kind of the local minimum, we notice that these particular modes are more in antiphase. to each other. This is merely observational. We don't have a good understanding of this phenomenon, but it definitely warrants further investigation. And this pattern is consistently observed for other sequences and for other extrema as well. So yeah, like I said, the top was the local minimum, the bottom was the maximum in this plot. Okay, so moving on to some conclusions. So just to summarize what we've done, we've evolved 274, so there's a lot of simulations, with mass ratios 2 to 3, 1 to 2, and 1 to 3, spread across 4 different sequences with 2 different codes, GR-Trumbo and lean. For all sequences, we observe oscillations in the kick as a function of eccentricity or the tangential momentum, with the global maximum at roughly E is 0.5. And these oscillations differ from that of the oscillations observed in the final spin and radiated energy. We posit that this oscillatory behavior is due to the change in the Infor direction relative to the apo or periapsis. And we find that longer inspirals lead to bigger and more frequent oscillations that we see by comparing our short sequence and our long sequence for the mass ratio 2 to 1. And we also observe shifts in the phase of subdominant multiples of psi4 relative to the dominant 2-2 mode between larger and smaller kicks. So what about any further implications or future avenues? So what does this mean? So our longer simulations gave us a more sensitive dependence of eccentricity. What about the circularizing nature of gravitational wave emissions was my first question. I don't know. I don't know what effect this might have. In certain astrophysical scenarios, for example, some 3-body systems, we might expect the interaction of the third body to retain or even increase the eccentricity of the binary, and this could outcompete the effect of gravitational wave emissions. Furthermore, actually, even astrophysical media such as accretion disks may further enhance the eccentricity as well. We need to investigate more quantitatively the differences we observed in the gravitational wave signals, as there may be implications for parameter inference in future gravitational wave observations. We definitely think there should be a study in using post-Newtonian methods to investigate longer eccentric inspirals on more astrophysical timescales. Obviously, in astrophysical scales, these simulations were very, very short. I guess the main takeaway from this is that the phenomenology of gravitational waves from eccentric compact binaries is very rich. And with more advanced gravitational wave detectors on the horizon, promising increased sensitivity in certain frequency bands, the need to understand this phenomenology better is only going to grow. So yeah, that's the end of my talk. Thank you very much.
Thank you, Miren. And before we proceed, let me ask everybody to turn on their microphones for a round of applause in retribution to your very nice talk.